Okay, until now it was quite boring. I hope we'll arrive finally at some interesting stuff. Let's see. Um, we want to arrive at some time to a theorem that we have stated about the dimensions, whatever it is, where suddenly in this abstract setting of vector spaces and linear maps between them, there arise numbers, so kind of quantification of these abstract concepts, which is remarkable. Okay, well, definition, dimension of a vector space. Let be a k-vector space, and its dimension is kind of a minimal number of, in some sense, independently representing vectors that we need to represent all the vectors in our space in some natural way, right? To represent all vectors with exactly that minimal number of vectors. Let D be k-vector space, then a subset E1 to En subset of V, and being fixed, of course, natural numbers is called a basis of V if span two conditions, span of E1 to En, which is defined as the set of all linear combinations of this piece. Clearly, that is inside of V. Okay, for that we need, of course, the i's in K. That is just the from the language expression, right? Lambda i's in K. Well, the proper writing would be all I element n lambda I and K I element V. Clearly that is in V just by the property of closeness of scalar multiplication, by the property of closeness of addition, right? As lambda. Right, the i's as in V, right? And properly written that is stated here, right? That's the first property. Wait, what property? Oh, that is in V, but we want that every element in V should have such a representation. So a linear representation in terms of these vectors, right? Why linear? Well, you recall linear function ax, ax on R, and here we just add those linear functions. So adding linear functions, you recall that is still linear, so this is addition of linear functions, right? And this is why it is called linear representation, because it's kind of a generalization of the most simple linear function from R to R, right? So, and another property, one n are linearly independent. Well, of course, you have to clarify what linearly independent means. And here for that, we have another definition. The 1 to the n are, of course, elements of some v. V is just by default a k vector space, right? And okay, I quote linearly independent when 0 has a unique representation f if I just have this I, and here is an index I, and here is I2, and here the vectors are numerated from 1 to n, then obviously this sum goes from I equal 1 to n, right? Equal 0 implies all of the coefficients equal to 0, so obviously a trivial representation for the 0 vector would be to choose the coefficients all equals to 0. But now we want that this is the only possible representation of this 0 vector in our space. Right? And this means if there is such a thing like this is a general statement with an application, that means, of course, whenever we have an object with a structure, that is, we can choose lambda i's as any elements in our K, we always will have lambda 1, lambda n to 0. Well, no, if you are already used to that, that means properly written for all choices. Wow, actually, okay. Totally properly written. That actually is written like that, but of course I won't do that anymore. It's just for now. Totally properly written. You have lambda 1 for lambda 1 in K, for lambda 2 in K, for lambda 3 in K, so on, for lambda n in K. This, of course, will be always shortened when it is objects from the same structure. It's totally clear what is meant, right? This will be always shortened for lambda 1, lambda n, or almost always at least, in K, something called. Right, what exactly? Well, exactly that. It holds that this being equal to 0 implies that our choice was already 0. So no matter what we do, those vectors have the property that no matter how we choose that, if we go through all the choices, we always won't find any choice other than zeros. We can try out all the possible choices of such lambda 1, lambda n, and no choice will give a zero vector except for the choice that all coefficients were already chosen as zero. But mathematically, of course, you don't think in that way. You think in the way of implication, right? Because it's much better to handle for mathematical reasoning, right? So we should get used to it. Right. All right, and that it is really the proper definition of linear independence. Well, that you'll see in a second. We call it remark. Definition of linear independence is given. Independence is given. Makes sense. The vectors being, and here it's better to look at the opposite to understand why it makes sense, being not linearly independent means we can choose lambda n such that not all of them are zero, but then there is I one of indices I, right? With okay, let's call it I tilde, right? I tilde, we said, with lambda with index I tilde is not equals zero. Then lambda I tilde the I tilde is equal to j. Well, let's do not confuse ourselves additionally. So I equal I tilde, that is some summing over all of 1 to n, but I'm omitting the index I tilde, right? And I and so you see I have just okay. Okay, can't do that, of course. I should do that. Of course, I have just brought everything on the other side, and we know how bringing on the other side functions rigorously, right? From the previous times, right? I have brought that all on the other side, and I have written that as a sum after having brought it on the other side, right? And And that's why here's a minus, because I had to subtract on both sides, right? Had to subtract, and there we minus rows. Right, and then obtain III children is equal, and I just divided on both sides by lambda I children here, right? Alright, and each amount that arises, and this is now the sum over this omitting I children and going through the i's. Right. So what you see that if the vectors are not linearly independent, then at least one of them can be represented as a linear representation of the other ones. So as a linear representation, so like here, so non-linear, being not non-linearly independent kind of means what it says, right? There's no independence. This vector can be already determined using the others, right? When we have such a choice of lambdas, right? Now, of course, when we have said something like above, have given such a definition, we are very interested in whether such things, bases, even exist, right? There is a vector space with a basis, you can guess, of course, or when a basis exists and things like that. We are very interested. And we are also interested, of course, is it unique? Because if it is not, those representations, they are not unique also. Maybe something about it is unique. But the number of vectors maybe needed, the number of vectors, maybe the minimum number, the maximum number, maybe number in total, because it would be kind of not nice to have representations of different, to be able to represent our vector space with different number of terms. Yeah, well, let's look at that. Okay. Examples of vector spaces with clear bases. Of course, we'll get to the real stuff about bases later with proofs, but for now, just to get some intuition, let's look at that. Clear bases. R3 has, oh, probably you're familiar with that. Oh, okay, I wanted to have Rn, but you can guess how Rn goes. A3 where U1 is of course first unit vector, A2 is second unit vector, E3 is third unit vector, is a basis of R3, even called a standard, the standard basis, even called the standard basis. Well, not quite, but well, it is called that, but it's not the whole truth that it can be even called the basis, but well, you don't go into it for now, right? Okay. You can guess how it works with Rn just the same. And you can see, of course, any vector in R3 is just some x, y, z, and by rules of how the vectors here work, you can just multiply x by this, you get x multiplied by 1, multiplied by 0, multiplied by 0, here 0, 0, here x, yeah, here you get y, here you get z, then you add that addition x plus 0 by the rules of component-wise addition vectors 0 plus 1 plus 0, 0 plus 0 plus y, we have multiplied by that, right? Plus 0, 0 plus 0 plus z, yeah. And linear independence, well, same thing, essentially, you just write this sum x, y, z in R, and you set it equal to the 0 vector, and then you get x plus 0 is equal to 0, component-wise, 0 plus 1 plus 0 is equal to y, and so on. And you should recall that equal vectors are exactly those vectors in this representation whose components are the same, and vice versa. Components are the same with vector cycle, so we have equality to the 0 vector. You have to have all those three sums being all those vector i's and sums. I mean, of those sums of respective of components of respective vectors taken like this plus this has to be equal to 0, where here is x, and so on. Right, so you can see that this is basis. Of course, same works for matrices. You just take those matrices with 1 and 0 everywhere else, 1, 0 everywhere else, and so on. So that's boring. But let's take the vector space R of x, which we define simply formal sum. We can define it rigorously. For now, we won't do that. But of course, we can define it rigorously. But for now, it's just formal sum. Right? You just write it as a sum. You could also write it out, right? N, where n is taken to be sorry, of course, by 0 it begins. We allow constant polynomials, of course. Right, n is in n. And what do we have? We minus usually have that this denotes n with 0, right? Okay, n a k r, and then for k, and this x is really a variable, right? Well, you must know, I'll tell you how to formalize this. What you can do is just to take the space of Rx is actually the same thing as the space of all sequences, like call sequences of real numbers, and such that oh, that finitely many and equal to and 0. Of course, we mean by that and using R now, right? And you can see that it is actually with polynomials if you just think how, well, of course, this is now a set with certain formal elements, right? Defined simply formally. That's a formal sum where you just work with it like with a sum, like x is actually variable, right? So addition on addition r x. How do you do that? Of course, we just go and do the formal sum. What does it mean, formal sum? Well, that is we work with a structure of a sum like it would be sum of numbers and variables. We just pay attention. Of course, we want to define sum, so it's plus sign here, right? This is just defined as the following thing. This is defined as sum from, wow, how it works. Well, the thing is, we have first the minimum of m, and then, and we have here some j 0 to this minimum. That is, I'm just summing that up until the year where both sums still go. So for example, if m would be the minimum, then n would be larger than m, and then this sum would have more sum terms than this sum, right? Or the other way around, in the case when n is smaller than m, right? And here, obviously, this is distributive law where we consider x like a variable, right? xj, and here plus, and here the remaining terms come, well, that would be maximum. You can always compare to numbers, right? All right, and here we have the minimum plus 1. So I just start to sum from here where the sum that goes to the smaller number ceased, right? Because I have to add those additional terms, and that will be j. Well, okay. I think I will now make a mess out of it, because I'll have to make all dependent on what is smaller and what is bigger, and this will of course be a mess, right? Well, let's do it like that. Let's just, okay. Well, I think we have just assume now, assume n is like, okay, I don't want to do that. I want to do that in a general way, but as you can see, I have trouble because, yeah, I don't know how I could do it independence on that. It's just, well, okay, we have to do that or else it won't work. Okay, sorry. Well, you see, we could have the two possibilities. I mean, this is two different possibilities, right? So here we have just aj, xj, if, and then of course we can replace max and min, right? If m smaller or equal n, then this is what goes after. That goes after that, right? All right. So that goes now. And this sum goes until m. Sorry, I have to pause a little because there's something. Okay, let's continue. Where were we? Right, if we have that this is that, and of course here we go qn, and there we have just left off this sum there, and here we have m plus 1. Here nothing terrible is happening. I have just written down it because I didn't want to decide that, well, let n be smaller than m, but in real situation, you have just to look at what you have. For example, you would have x to the power of 3 as the uh, highest exponent here, and here you would have x to the power of 5. And this is the larger thing, and you have just to apply this rule, and you see that this is completely natural. It's actually, it's nothing difficult. It's just looks difficult when I write it in such notation because it was actually a bad choice to make such a case distinction, but well, why not? We can do that. Okay, and you see, maybe here it is even easier to see when you have such a thing, right? You have like 0, and here, wait a minute. Yes, exactly. And here, keep in mind that something like sum from I equal t to r with t over some, I don't know, over whatever actually. A, oh, okay, let's not take A, take ci, and t is smaller than r, t is, yeah, more than r, it's just equal 0. So we can't sum in the other direction, so to speak. If the lower index is smaller, if the lower index is larger, the upper index, if it is smaller, of course we can just go through, but if it is larger, then we don't have anything to go through, right? So, particular if that larger than that, we would just have here a 0, right? Well, in what case that would be larger than that? Well, when min and max are just equal, it would be the numbers are equal, and this would disappear, this would disappear. So it would make sense that we would only go to the number n or m. Doesn't matter because n is equal to m. So yeah. All right, and here you can see that in this representation, a2, let's say we go just like there to an, and then everything but that means we go through natural numbers and there only zeros are to come. And here, oh, let's do not try to be as general as possible, just be content with taking what is, right, be true. So, and here we have bn, and here we have bn plus 1, and here we have somewhere bm, right, and then zeros are to come, and then zeros to infinity, right, and then we add that, and you see we just add v positions, right? So this is nothing than adding v positions. The only crucial thing here is what comes in what slot. What comes in slot 0 here, what comes in slot 0 here, and you could just think that here you have x to the power of 0, here you have x to the power of 1. So the meaning of this is exactly as the meaning of this, because structurally it's exactly the same thing. The same things happen, right? This is just like a position. But of course, with polynomials, you can do interesting things like you can plug in something as a number, but here you could too, because you could just define that you multiply this vector with a large infinite number of zeros to come with a number, with a real number. Like you could take r, and this is infinite vector of r. You could multiply that just like a scalar product. Scalar product, Euclidean scalar product, you probably know, right? You can do that. So that's actually the same thing, right? And you can guess how scalar multiplication is defined. And of course, it then defines vector space, which I leave to prove to you. Scalar multiplication, of course, it's defined like that. You just plug in this lambda. So it's actually pretty much like you treat those variables and those scalars just like you treat numbers and variables by computations, by some equations or something, right? Right, and you can check yourself if it is a vector space. Oh, what we wanted to look at, we want to look at the basis of that. We observe that x0, x1, x to the power of 2 is an infinite basis. Basis of Rx. Well, and what do we mean by basis here? In our definition, we only had that basis is some finite set, right? But well, this is like a more advanced notion of basis. This basis is also important, in particular if you want an example in quantum mechanics. Infinite basis of Rx, where return basis is. Oh, you just see that you can represent any polynomial as a finite combination of those, right? Is construed to mean oh a set, possibly infinite set in the given vector space such that any element of this vector space can be represented as a finite linear combination of a finite subset of this set. Alright, so if we have for vector space V base K, V K plus such a basis as set. Wow, that's just a set X. Some index set that's not necessarily number, that's just some index set, right? Some index set that could be real numbers or whatever, just some index set by which we can index this elements, right, in the such that for the element V exists J subset of I finite with a property that they exist lambda 1 and let's say lambda J, we said that it is a finite set, right? So we can just say that it is equal J, right? We just call these elements like that, because the important thing is the existence such that the is represented as a sum with J. Okay, there exists that which is equal to okay, sorry, that was of course wrong. Just is not J, that's object of different kind, such that 1 J is equal J, and there exists V1 Vj so exists that, there exists that subset of xi I and I with a property here, the quantum expression continues, right? With a property that you could guess, and I equal 1. Okay, let's not call it I, same context. 1 J. Alright, J Vj is equal D, and this is the set, right? such a set that for each v in D we can and course and that's first property, and another property of that a subset of V that to be basis and such that xi, I, and I are well linearly independent, which means here just that any finite number of the vectors taken from here are linearly independent. It's often the way to define some quite intangible things in mathematics, to just always take any finite number of something if it goes far beyond the normally handleable infinities, right? So, but you don't need to concern yourself now with this definition. It's just to give an impression what also exists, right? Right. It's quite clear that it is a basis. You don't need to think about it extensively, but of course, if you like, you are welcome to think about it, right? It's actually quite simple. You just, well, probably if you want to check that it is a basis, of course, the corresponding thing to that in the other representation would be exactly the sequences infinite 0, 1, that is 1, 0, 0, and all zeros, right? Infinite 0, 2, and so on. That would be correspondence in the space R X in the sequence representation, right? That would be 0, 1, 0, 0, right? And you would continue this, right? If you want to check that it is a basis, you could use this representation and check that. Maybe you could just think about how that actually works with that. It's just that x0 is not the same thing as x1 and so on. So yeah, I mean x to the power of 1, I just call it x1, x to the power of 2, x to the power of 3 is just different things. And you can see that because, well, you can construe them as functions. For example, like x0 is your line, the height 1, right? For all your numbers, it's just 1. And this is not the same function as x, which is, well, okay, of course, it's not x, sorry. Okay, sorry. Yeah. That is something like x, that is 0, that was x0, is x1, and that would be equal if you would have equal values for all those, so you can consider them as functions. That is also valid mathematically. We don't discuss it now, but it's actually quite valid. Right? Well, at least in some contexts it's valid. It depends on what you plug in, so to speak. Right. All right. Example for R, if you plug in elements of R, it's valid, just like I'm doing now. Now you have x squared. Of course, it is some f1 of x, this is some f2 of x, this is some f3 of x, but just giving you a visual intuition, right? And they are not equal, so you can guess that if you have something like 1 plus x, I don't know, 0, this is supposed to be a linear combination, right, of this and this, now considered formally, but now you look at this picture and you think, well, this would be equal to 0. Okay, of course, sorry, we have to have some lambdas, right? Or a1, a2, some coefficients in the field, in that case. And you think, well, in what case would that be 0 for each real number? This is how you compare them. You can think of them like that. Of course, formal comparison is something else, but you can just think of this formal comparison in these terms. And you have this linear combination, and you have kind of, let's say, 2x equals 0 for fixed, a1 and a2, and x going through all real numbers. Well, you can think that no matter what real number, no matter what coefficients you choose, it will only be the case when, I mean, for all x in R for fixed R A1, A2, this will only be the case when A1 and A2 are above 0. It kind of means linear independence if we consider here linear independence in terms of functions instead of considering that in terms of formal representations. All right, well, or you could look at this representation here as you wish. Right, so this is another basis. And you know if we should consider another examples. Okay, yeah, we should. I think we should. Well, okay, let me see. Let me just say II.III. Right. Now, let me think for a little while. I would like to show you something, but I'm not sure if I should. Oh, okay. Oh, let's consider, let's consider a field K as a vector space, and you recall it is a vector space. In any K, and K is a basis, well, and a vector with itself is naturally linearly independent unless it is a zero vector, because if you have just lambda v and this is your I equal 1 to 1 and that's 0, and this is just lambda v and that is 0, and well, then 0 above is 0, and if lambda is not equal 0, then v has to be 0. Oh, Why that's the case? Because suppose lambda not equal 0, v not equal 0, and okay, let's see. It should be something simple, but right now I'm a little bit sleepy, so I don't know. Well, it's just that. Okay, that's really simple. Sorry, we can just divide by lambda both sides. And by the way, that's of course the inverse element of the multiplication, which we do not like that, right? The inverse element of the multiplication in a field is denoted like this, and this is not a fraction, but this is the inverse element of the multiplication. This is also the inverse element of the multiplication. This is not some kind of defined exponentiation. We have not defined it, right? Only for R we have defined it. So yeah, this is a general field. So this is inverse element of multiplication. And we can multiply it. And we obtain, of course, inverse element of multiplication multiplied by lambda gives you the 1 in the field, 1 in the field multiplied by v gives you v. So this is v equal 0. Right. And if v is supposed to be non-zero and lambda is supposed to be non-zero, and we assume that we have this equality, then we get a contradiction, we get v equals 0. So the only way when v is non-zero to represent 0 is to get lambda equal to 0, because lambda non-equal to 0 gives a contradiction, right? Alright. Right. Contradiction. That's the sign for a contradiction. Right. Right. 2 v non-equal to 0. Right. Okay. And wow, so k itself is linearly independent, and obviously any for k have equal well what k multiplied by L divided by k. And of course, this element is again not a fraction, but this is L multiplied by k minus 1, which is element of the field. This is multiplicative inverse of k. This is just L, and we have k multiplied with this element. And this, of course, L, because multiplicative inverse plus commutativity, abelian group with respect to multiplication field. So yeah, we get L. And this proves that any k is a basis, right? All right, what do we do next? Right, that were some examples of bases. Let's get some action. Well, can we start right off the bat? I'm not sure. As I told you, it's a spontaneous experiment, so I don't know if we'll be even able to prove it right off the bat. Maybe we need some auxiliary results. But well, it will then turn out eventually within the proof. I'll see that we can't advance at some point, right? Okay. Right, well, what do we have here? Theorem. First clarify some issue. just about existence of a basis, right? The assumption, that is an assumption, that a special kind, we won't go into it, of a basis exists for every vector space. Turns out to be equivalent to the axiom of choice. Turns out to be equivalent. And if you don't know, the axiom of choice is result that can be assumed in mathematics that need not be assumed in the mathematics, but actually many nice things, beautiful things don't work without the axiom of choice. So the standard is to assume the axiom of choice, but actually mathematics is consistent with or without it. There are no contradictions arising, and this axiom was very debatable at the time when it turned out what consequences it could yield, right? Like Banach-Tarski, paradoxon, you can separate a ball into balls of equal volume, uh, two of a number, and well, it's kind of funny for that you have to cut this ball in a certain way. And if you cut the ball in this way, you can just reassemble with balls, two balls of exactly same volume, identical two balls. You have reassembled one ball into identical two balls. Would be nice, right? But well, that's only within the mathematical realm. But when such contradiction to our nature, intuition arose, well, not all people were happy, but well, by now, just accept that mathematics is quite an abstract world, which does not necessarily always coincide with the physical intuition, which is just a given, and many beautiful results actually rely on this axiom that is completely non-constructive. But without it, our mathematical life would be much poorer. So yeah, turns out to be equivalent to the axiom of choice. So that is really an assumption. That is not a theorem. That is just an assumption within mathematics, right? But we don't need to concern ourselves with such things. It could be a theorem proved based on some assumptions, but yeah, there will be somehow the axiom of choice involved. So usually we assume it is, so usually we could assume always that basis exists for every vector space. Oh, respectively, we could prove it having the axiom of choice. And if we would assume that, or if we would manage to prove that, then it would mean that we have assumed the axiom of choice, even if we didn't know that we have, right? It's an interesting thing, actually, but okay. No need to get concerned about that. Well, that is actually in our mathematics, in the mathematics we are uh, quite happy with. Um, a basis exists for every vector space, but a special basis, right? And other than that, it's just definitory things concerning the existence. We just say, right? Definition. If a vector space has a finite basis, that is to know if it is the case we have to establish or not. a finite basis, finite numbers of vectors like defined above, has a finite basis, then it's called finite-dimensional. Okay, if a vector space does not have a finite basis, it's called infinite dimensional. And this infinity is not necessarily this infinity, but it could be also this infinity. And this infinity is larger in some certain sense. That is no bijection. It could be this infinity. That's the power set and so on, right? So it could be anything. It's just called infinite dimensional. Well, what we have here with the polynomials, it's kind of special case because we can handle it so easily, but well, we won't distinguish it especially. We'll just know what we can do with it, right? Right, okay. Theorem. And now we'll see if we can prove it. Theorem. Any two bases of a finite dimensional vector space have same number of elements, and if it is a number, it's finite. And in particular, it's finite. Okay, and we call such a number dimension of the vector space. For a vector space V right dimension V. So you probably recall from our theorem from above, we have established, the theorem from above where we had some certain quantitative expression for some dimensions of spaces of kernel of image of a linear map, and then of some vector space of the domain space, namely this is the dimension that is involved there, right? Dimension V for the dimension of V. Right, but now we have to show that the dimension is actually well defined. It would be bad if we would call it dimension of V, having the object V, and it could be two bases with different number of elements, then we would not know what number it actually is. One time it would be one number, one time another number. Wouldn't be nice, right? Wouldn't be well defined, as a mathematician would say. Okay. So, have to show that they have same number of elements. Right, proof. Let me one n w1 wm b two bases of course a finite dimensional, since a finite basis exists, finite dimensional vector space V. That is, they are both subsets of V. They're both linearly independent, I mean respectively, and they both span V, right? It suffices to show m bigger or equal n, because then also n bigger or equal m, because we do not specify anything about the spaces, so we could just switch the rows, right? We would also have automatically n bigger or equal m, because the arguments would be symmetric, because we do not specify anything special about those numbers. It's just some numbers, right? And this is just some basis. There is no asymmetry here, right? Suffice to show m bigger or equal n. Oh, suppose, and here the spontaneity, what spontaneity comes because I don't know how to show that. I'll have to figure it out myself. Let's see if I can. Okay. Suppose m is smaller than n. Wow. Then that is, we want to make a proof by contradiction. We suppose that it is the case to show that it can't be the case. Then since call it just BW, this is just BW. And since BW is a basis, have the I, there's just those three, have for the I element B D. Okay. Then they exist. I Okay, well, let's call it A1, J, A, alright, we have N, J, well, no, J goes through that, so that would be MJ. Actually, why J? I need to have I. Okay, well, that's actually J, right? You see that is for VI, right? VI, and we go for I, for I, so this we would have N, right? And for each such I, we have respective A1 to AM to represent him with respect to the W's, right? W I is fixed for V, right? Of course that's not 1, it's J. We want to go through J now for fixed I, right? Alright, so, and those coordinates could be, oh, those coordinates, those coefficients, they could be different, so that's why we have to index them that way to capture all the generality. Right, and what's that? This is representation of AI. Right, then everything can be represented like that. And those vectors are supposed to be linearly independent, right? So, well, we have to use that this is more that, well, how do we do that? That's a good question. Let's see. How can I show that? Well, have supposed that m is more than n, and how? We'd like to show oh, let me think. Okay. Let me try to do it like that. Um, we show that one, let's call it sigma, that is, this is some mapping of this. Well, yeah, that's not right, because we'd like to have that, right? But let's well, how should I do that best? We'd like to show that already m of the d vectors suffice, that this already follows, and then we would think what we will do next. We show that. Okay, we'll do it easy here. The R1, the M subset of PV. So you see, that's exactly M of M, but I don't know with what indices, so that's why I have to keep this indices general, but they are M of the number, right? We should have such that, let's call it BR, such that BR is basis of V. Right, how do we do that? Wow. Let's see. Okay. Well, for okay, I don't think we'll need that. It's the other way around. For WG and element PW get WG is equal I equal 1 A I J E I percent. Yeah. Okay. And that's 2m. We have this sum 2m. From AIG and K, our vector field, our our field, right? For some aij k. And oh, now I'd like to find possibility to replace that by some vector, right? Well, what do we have here? We have here the sum, and we'd like this to replace this. We'd like this to work there, but in general it won't work, right? But for sure the question is why we can find a single vector to replace that, right? And the answer is well, of course it wouldn't work just like that, right? We would have to replace the this the w's by this, or at least that's our idea, but it doesn't seem to work quite nice, right? Or maybe we have started off too early without some auxiliary results, but that's the point of it. So that's the point, and we'll see if we manage to prove what we set out to prove. All right. So now have to think about it clearly. So we have two bases and we have to show that the numbers of vectors in them are actually equal. Alright, I don't see it yet. So let's see. Okay, I didn't think that will be already interesting, but it is. Right.
So yeah, you can see finding proofs is not always easy. It's actually the most interesting thing. So I have assumed that right.
What will do? We'll try to supplement and okay. Okay, let's try to supplement it. And try to replace some base by W.
Alright, and that this pen will remain the same if we add some v is clear. The question is, why will it still be linearly independent? Well, W1, W1 are linearly independent. So they are linearly independent. So W1, W1 is linearly dependent only as and one, right? any vector that we take on basis BB, these vectors will be linearly dependent. Right. Do we have then? Okay. Now recall that V was basis, right? Hmm? Now recall how we represented it. And recall it WJ AIJ from I equal 1 to this of course wrong because that was n, right? Right, V1, Vn. Alright, that's n. Wj is equal to Aij Vi. Okay. Now Wj equal Aij Vi if I going right, and hence okay, let's go like that. I equal 1 to n Aij 1 d. Okay, that's g, right? G equal why d? Why do we need additional stuff? We just go to go. I would just want to go all of them, right? So, right. We need same chase and this of course, right? This is of course I. This is j, and j goes from 1 to n. And we need also lambda because we have a representation, right? I'm just writing down the linear dependence of those vectors together, and I'm using this representation, and this is just some according to this representation where I have just brought in lambda m from here, where this will be just definition representation that I have. And this is here. This is just separate term, right? This is equal to 0. Right, and we have brought in this kind of representation. Which results, of course. Oh, okay, right. We still need some else because we need this is here, right? So this is different things, right? So for let's reiterate what we do for each s. we take as vectors w1, wm, and vs. So we take w1, wm, v1, w1, wm, v2, and so on until vn. Each that choice gives a sequence of vectors where m plus 1 vectors are in it, right? For each such choice, we get coefficients for those vectors, making them equal to 0, so that not all coefficients are 0, right? And here we can plug in for each such choice such representation of a respective vector w. Actually, ij would not depend on s, because this is just a fixed representation, right? And for each such choice with an s, we just get that we have specific lambdas, and lambda is of course not an n, lambda is in g, and lambda weight in g, because we have lambda as is an index for each choice of the v in this sequence of vectors, and j is just going through all of them within the choice for all w's, right? And the w is just represented like this, so lambda is j will be actually here, but we have taken it into the sum, which we can do first, and just the distributive law, and this gives 0, right? What does this give? Well, if you pay attention, you will notice that what we have obtained is exactly, if we consider linear independence of those VI's, right? And for each I, we have obtained from those different choices of S, we have obtained that lambda G S A and G, right? And this is that choice where we just take our I fixed, right? And we just take j from 1 to m, right? What we do here is just to fix an I and to look at the sum in the cross direction where we fix an I, and for each j the I is fixed, and we go through the j's, and this will be the coefficient of the I in the j, the I of course, the I in the sum. We could also switch the sums simply, and you would get the coefficient of the I, which is given as such a sum. Okay? And this is for s, and this is equal to 0 for s element 1, 2, n, or what? 2n, right? And this is now equal to 0, right? We would have matrices that probably would be quite easy. I mean, we would have some special properties of matrices, right? But we want to do it on foot, Oh, sorry. I have not paid attention. We have not like that lambda s is equal to sorry. I'm wrong again. You see, those vectors are linearly dependent, this vector is linearly dependent, those vectors are all linearly dependent. Ah, okay, now I see. Here, of course, that's not quite true. And this is for the vectors G. For the vectors I. Okay. And this is for the vectors I. Which are not equal to this. Right? So here we have S fixed in 1 to n. And yeah, here we have again 1 to n. And here, of course, we have to at the point I, in the point S, we have to add something, right? So this is for I not equal to S, y equal to S. We have to have J equal 1 and then J S I S J plus S, right? Because that is the S vector, and here we have this vector as well. But here is okay. I know that's okay because it's all sums, right? So that is equal to 0. Alright, this of course gives this so this is for I not equal to S, this is for I equal S. And this, of course, allows us to actually have wow, wait a minute. This is just showing EIGs. That is for I and equal S. Just have that 0. And for equal S, we just have that being equal to 0. And with that, your team well, I thought that somehow we will get the rule linearly dependent for any S. We should actually get a contradiction, right? it is like okay, I get that lambda is the coefficiency, right? And you would get that you have this minus and you would get being that being equal to 0, right? There you went through each 1 to n, right? And it out that you will rise a contradiction for linear dependence of m, but doesn't seem to be the case. Okay. Well, that doesn't seem to be the case, that's for sure. So, we have assumed that they are linearly dependent, and we have just gotten that they are independent with no problems, right? Seemingly. Now, if all of them are linearly dependent, really, and you just have that, right? So you'd have here's something funny about it, right? Something quite funny. It's just that you can have if you take that is actually coefficients, maybe double, isn't? So for each s, we get that. For each s. Hmm. Well, it's just that it is kind of funny. Or maybe we started too far away, but well, that's the point. The point is exactly to start like this. Let's see. How can we do that? And just the two bases. And I'd like to have n is bigger or equal n. Right. So let's think about it properly. We have m is smaller than n, which we would have here. So start to put it like that. So W1 okay. We have W1 is actually represented like a sum. I I equal 1 and right. try to find a way to, well, then use number I children and number number when children equals 0 since w1 not equals 0 because we wouldn't take up 0 vector in the basis because it doesn't change anything in a linear combination, so we could just assume that all zeros in a basis are discarded. There could only be one. So, yeah, so same vector in a basis also doesn't give anything because we could just use distributivity law. So, kind of assume that it is not the same vectors, right? Right. It is not zero. Right. And of course, so there has to be at least one answer. Then what we do next? I want it. Actually, okay. Non-equal to I2, right? And non-G, G. Right, alright. Then we think so. Which means that the children can be replaced by Theorem and lambda I children plus j equal to 1 and j equal children num j bj later. And we kind of claim, like to claim and claim and our one Let us we omit the tilde here. That is like omission, right? Then yes, yes, of course, yeah, linear independent. Suppose they are not, then another one equal a two lambda t. Okay, lambda t. Let's call it lambda t theorem, right? One t equal I theorem. Then yeah, exactly that. And well, that is for some lambda t theorems, right? Okay, and then we get what? Oh, get from star that yeah theorem one and theorem is, or you could just say v1 to n are linearly dependent, right? Because you plug it in star, plug in this expression here, and you have just the sums. You put the sums together, and you get a representation of the tilde with some coefficients lambda, with sums of coefficients lambda, which will not all be zero. Why is that the case? Oh well, doesn't matter if they are zero or not. We have just represented this vector, and it has the coefficient 1, so it's particularly not zero. And we have here the sum of all our vectors in the basis V, right? And here we bring that to the side, and we get the representation of 0 with at least one coefficient here equal to 1 and equal to 0. So yeah. Indeed. W1 1 n n yeah, information I children are linearly
independent.
Right. Now,
Okay. Span W1 emission Theorem simple span PV. Already called that PV was just the vectors V1 to Vn without emission, of course. Right. This is just obvious because if you have span of that, then you just have all linear combinations, right? But we have that here, so this is where we started. This was by the basis representation property. This is in the span, right? And hence we can just replace that span by that, and there will be some coefficient by here. Here that will be sum of our base in the basis multiplied by some coefficients, right? And hence that is subset of this. And the other way around, well, if we have something in the space of V of PV, and then we have the vectors including this, so this vector is now not excluded, and this is just some multiplied by some constant, and then this constant multiplied by this just gives an element in this one. And well, and you see that this will be exactly a sum. W1 is multiplied by something, and this sum of these vectors multiplied each by something, right? So this is true. That shows W1 V1 yeah. I mean, that's emission, right? Emission, not agent, but emission country. Yes. Base. Now we'd like to do the same thing for W2, right? For W2 in this basis. Now have W2. Because this is a basis, we have basis representation property. So we have that. G, G, G equal 1, and G emission, right? Not equal 0. Plus, of course, what we have emitted. Let's call it just VI just for fun. VI, W1, right? And now, of course,
suppose, oh, wait a minute, suppose that II is not equal to 0. Then my representation property of b double, right? Any vector can be represented with respect to b double because it's a base, because it's a basis, right? In G, and shortly being able to be represented just means it's in the span of b double, right? It means exactly that's linear combination because elements of a span defined as linear combinations, right? For all in G element B mission I children. Wait, that won't work because no, it works of course. Yeah, doesn't matter. Oh, prediction in any case. That's the thing. Okay. Right. Should be unless that's all 0. This is not 0. Right. So we are able to replace that by W something, and should be able to represent that. Right. Because we have the representation property. Right. But in any case, to have some representation for that. Yes, of course, but this representation will contain W2. Okay, yeah, okay, works. Okay, 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 okay. ones, no? No, I'll do it differently. Now, cannot have and zero lambda actually limited. Alright. W2 equal II.I W1 contradiction to linear independence vectors in BW, so the code BW was base, so linear vectors here v vectors in here linearly independent of vectors in BW. Okay, so as above, can obtain basis well, W1, W2, because the vector which we choose is not W1, so we specifically choose not to replace W1, but to have W1 in our representation, right? Just like before, we bring W2 on the other side, just like we have done here, right? Of course, have to have minus somewhere, but it doesn't change anything because it's just, well, the respective constant will be multiplied by -1. But here, just like here, we bring on the other side, just like here, bring on the other side, that was brought on the other side, right? Or we could say, well, that was brought on the other side, and that was brought on the other side. Right? We could just change, for example, here multiply by minus, and here all be lambdas which change signs, so it doesn't matter, right? Now we do the same with one of the p's, and we do it explicitly with one of these. Well, if we wanted to correct that here, we would have something like, well, for example, minus on the chase, right? We could then just bring exactly this on the other side, and instead of lambda chase, we would have minus lambda chase compared to here, and that would go on, right? So minus or plus, it doesn't matter because those coefficients are arbitrary. Alright, this graph can obtain a basis a1 an, where we replaced already in the basis where the I tilde was omitted, and the j tilde now is omitted, where j tilde with that vector we choose here from here, one of those non equal to 1, right? So we wouldn't choose this, we would choose this, and this would be again in the representation as one of the vectors representing, and this will be truly replacing some vector v. That's what we want, right? Okay. Iteratively we proceed to W1 W we in here we have some other indices, right? But how many of them are n minus m, of course, until n minus m, right? As the obtained basis. So we do the same step in W3, we do the obtained basis, and we do same step with careful choices always, W4, and that way we get this basis, right? Okay. This is I with index 1, this is I with index n minus m. Alright. And well, n show that this contradicts W1 Wm linking basis by itself, that is taken alone, because that was our starting assumption, right? We have shown if m is more than n, then we can always do this replacement, obtaining such a basis where at least some few other vectors are contained, right? In the basis by itself. Well, that's actually fairly easy. We have the I1 W1 Wm linearly independent as vectors. Let's call it B W theorem vectors basis and basis B W theorem. Simultaneously have EI1 is equal to lambda p w p I1 p colon 2 n since w is basis. Contradiction. By the way, here we have used, you probably noticed also in other places, and actually you should have come up yourself with the conclusion that we have used that. You should have come up yourself with a hypothesis, and then you should have verified, disproved your hypothesis. Actually, if you would have done everything right, the hypothesis would be true. But let me tell you what you should have come up with yourself as a hypothesis. That's how math works. You just assume things and then you just try to figure it out if it works the way you assumed it. If it doesn't, it's how serious math works. But let me show you, and then just if vectors A1 ek now element of V, some k vector space. K, of course, we field are linearly independent, and so any choice of vectors M1 and R2 M1 2 assume the opposite then take J 1 okay some and J1 well n is bad children J1 to some I don't know G just numbers, you can call them anything, right? And now you have material. You have me material equal 0 with not all, and then insurance equal 0 and then just take lambda in tildes, and for remaining coefficients, other coefficients, zeros. So you just take same coefficients, right? For the vectors with those numbers, you already know that this gives 0 and not all of them are 0. And for the remaining vectors, you need to have coefficients for to have linear combination of 0 with not all coefficients being 0. You just take zeros to obtain zero equal to well, this section should be, I don't know, something like GG. You understand what I mean? Just some number of vectors chosen there, and you go through them, right? And theorem, theorem plus the b b base b. You just go through the other vectors which are not j j j j and j1 j. Oh, it's more difficult to write it down than the idea actually is. It's just that if already some of the coefficients are not equal 0, then we can fill them up with our coefficients. They still will be not 0, because adding 0 doesn't change anything. Our coefficient 0 will, and together with those coefficients, give a linear combination, so not all coefficients are 0, right? And this is why I can claim that those are also linearly independent, because if they would be linearly dependent, and those would be linearly dependent, and that wouldn't be a basis. Right, okay. This shows that our assumption n smaller than n is wrong, since it allowed, of course, usually you don't spell it out, you just see that the conclusions from some premise don't work, and you conclude that work means there's a contradiction, then you conclude that the premise was wrong, right? If you assume that our premises are well defined, proper, which is the case here, right? Premise that was somehow that somehow led to a contradiction was this. I mean, our premises we just want to keep, it has to be vector space, we want to have two bases, so it's just differentiatory premises, so to speak, and this premise that we add to that, to the situation which we had that yielded a contradiction, since it allowed for construction. Well-defined proper construction. Well-defined a proper construction leading leading to contradiction. So, and hence we have biblical. As I told you, since there is no symmetry between the two bases, there are no additional properties assumed. You can just swap with rows or do all the same arguments for bigger or equal m, but this will be simply all the same arguments where m and n are swapped, so there's no need for that. Well, so by this proof I had some trouble. You have seen I have started in a way how it didn't seem to work, right? But well, eventually we arrived at the conclusion, and that was fun. This is actually what mathematics is. Mathematics is thinking about proofs, coming up with proofs, understanding why they work, why they don't work. I mean, own proofs that came up with, why it works, why it doesn't work. Exactly. So this is real fun, mathematics. Right. But as you see, you need some tolerance against being frustrated when you do maths. Yeah, so the proof is finished, and this shows that the concept of dimension is actually well defined. Whenever we have a finite dimensional vector space, the number of the elements in two finite bases of the space, and the bases can only be finite because in infinite bases you can replace all the same elements. I mean, in a finite dimensional space, every base is finite because you can replace the same, and you'll just see the same contradiction essentially, right? Because the contradiction was exactly to have at least one vector more. That's already problematic, right? Because there's a contradiction between representation property and linear independence property, right? This shows that the notion of dimension is well defined. So that's really the well defined number, the number of the vectors in a basis of a finite dimensional space. This shows the given finite dimensional space, the notion of dimension of finite dimensional vector space is indeed well defined, and this is a remark maybe note, right? Note. Alright, with that we finally have the concept of dimension, and that's great. Right, okay. That's it for now. Thank you very much for your attention, and we'll continue next time. Okay, let's see.